Welcome to our demonstration of train. Let's set some context for our demonstration. In process industries, such as crude oil refineries and chemical plants, precise estimation of process data is essential for optimizing performance and monitoring yield. Accounting inaccuracies directly impact revenue and custody transfer applications within refineries, gas plants, and chemical product manufacturing. While conventional data reconciliation and gross error detection techniques address process measurement errors, experienced operators often estimate missing measurements or sensor errors through manual optimization. However, this method is time-consuming and relies heavily on the operator's experience. Train introduces a causal theory-based automated mass balance agent that seamlessly fits into the prevailing mass balancing process. Powered by the causal models developed on cumulative know-how, this automated mass balance agent autonomously recommends corrections for process measurements by analyzing various scenarios. Serving as a companion for process engineers or operators, this agent significantly reduces cognitive load, enabling quick and informed decision-making. This enhances overall productivity and can elevate mass balancing activities from an end-of-the-day to an intraday process. Let's take a look at train in action. In this demo, let's consider that I am the site-level operation lead at a petrochemical plant, and I spend approximately 2 hours daily on reconciliation tasks. So let's set the context of the user's problem. Here we are looking at the petrochemical plant layout, depicted by the network originating from Jetty 1, the point where raw petroleum is received as input. Following this, the raw petroleum undergoes processing in various units, including Unit 1 and Unit 2. Each processing unit extracts refined petrochemical products like gasoline and diesel, which are then dispatched to end distribution terminals 1, 2, and 3. Additionally, the network incorporates storage units, with Tank 1 being part of it. This entire network consists of 3 junctions and 6 routes. 5 routes are equipped with flow measurement instruments, while Route 3 still needs to be measured. Looking at an end-of-the-day flow measurement, we see an overall imbalance of minus 2.9 K units. How do we estimate where the error is and then reconcile that to the measurement? We face 2 computational challenges in the conventional error estimation and mass balancing approach. First, there are multiple ways to make corrections numerically. Second, the unmeasured route significantly increases the optimization solution space. So let's get a little familiar with the platform. Action 1 in the demonstration. To address the flow imbalance, checking both I and other experienced operators handled reconciliations. I'm looking at methods and diving into sensor details, calibration, sensitivity, and maintenance status. We've ingested all of these inputs into Train, and Train represented the cumulative knowledge as a causal model depicting the process flow. This workflow interacts with the causal models and guides me to systemically estimate errors and make informed decisions to improve reconciliation accuracy. How can the workflow help me systematically estimate the measurement error and finally reconcile data? Similar to a standard scientific experiment, my initial step is formulating hypotheses. I opened the step-by-step hypotheses generation and validation workflow. First, we load the causal model around the mass flow imbalance. We use Train's causal modeling capabilities to generate a causal model from the cumulative knowledge of the domain, process, and SME narratives. Now we are associating the 90-day historical data with the causal model. We have sensor readings from 5 routes related to the respective sensor errors. And these readings map error estimates to reconciliation and attach reconciled values to reconciled readings. We have a comprehensive causal representation of the imbalance scenario. Now, the mass balance application agent autonomously generates potential hypotheses that could be causing the imbalance. It then quantifies the individual effects of these hypotheses on the actual imbalance. The hypotheses identify the causes and effects of process, system, control, and sensor errors driving the imbalance. For instance, they reveal the role of sensor calibration and maintenance in measurement confidence, which directly affects the reconciliation process and adjusts the flow imbalance. Wonderful. So we have several hypotheses. In the final steps of the hypothesis workflow, the mass balance agent automatically narrows down the hypothesis list from 10 to 3. This condensed list points to the primary cause of the imbalance. First, the measurement on route 4, followed by route 2 measurement. Moreover, the error estimation at route 4 drives the error estimation at route 2. In the final hypothesis, causal intervention is crucial. Recognizing that a single measured value doesn't singularly cause flow imbalance, proper conditioning of other variables is essential. The agent autonomously explores various front door, back door, and instrument variable analyses. It refutes the derived causal effect against different stress scenarios, establishing the final validated hypothesis list. In the next step, I aim to understand which readings I can change more and which ones I should avoid altering significantly. The agent indicates that I can perturb route 4 the most, followed by route 2. Meanwhile, minimal changes are recommended for the other routes. The allowable perturbation depends on the 3 validated hypotheses. With route 4 measurement identified as the primary cause of the imbalance, the confidence in that sensor reading is minimal. As a result, the perturbation allowed for that reading is maximized, as shown by the confidence score and perturbation matrix on the machine interface. In the final step of the workflow, I initiate the agent's flow balance step. The agent successfully delivers a reconciled network reading with an imbalance of only 2 units. It adjusts the route most followed by the route and generates the flow measurement for the previously unmeasured route. The mass balance agent utilizes the confidence score and perturbation matrix to develop controlled perturbations until it achieves the minimum imbalance iteratively. Using the mass balance agent, my daily reconciliation, which was once a 2-hour task, now takes 10 minutes. The workflow's systematic approach has improved my efficiency and allowed for scalability in handling extensive network reconciliations. Since this process is repeatable, we can perform it again tomorrow or even as an intraday activity. It's a game changer, making my daily routine more efficient and enjoyable.